order of Taylor's theorem did we use to derive them? First order, right? So there is a formal term for these directions. They are called linearized feasible directions. Okay, so linearized feasible directions. How are they formally defined? This is script F as per Nocedal's notation. Okay. Is the set of all D. Okay. Just go back to how we have defined it in the previous case for the inequality constraints. When I had an equality, which was the first example, very first example, what was the relation between D and grad C? Look back at your notes. Greater than 0, less than 0, equal to 0 for an equality constraint. It was actually equal to 0, right? So D transpose grad C I x is equal to 0 for all I belonging to the equality set, right? So if I were in the equal set, then how do I move? I had better move. I mean, this makes in plain English also it makes sense, right? If I am in an equality constraint, then by moving orthogonal to the contours of grad C, I will maintain the same value of C, like when I am climbing up a hill. So this is equal to 0, that makes sense. And this is about equality. What am I left with? Inequality constraints. Inequality constraints, I think if I wake you up at 2 AM, you will tell me this is the condition now. D transpose grad Cix should be what? Greater than equal to 0. Okay. Now for all I belonging to what? Should I write inequality or should I refine it a little bit? Is it all inequalities for which this should be true? Think of the distinction between case 1 and case 2. What is the difference between case 1 and case 2? Active versus inactive. If I am inactive, think of it, I am way inside the feasible region. Any direction works. But if I am on the boundary, I had better be careful about this, right? So this is the intersection of the active set. Active set contained equalities and inequalities that are active. So I have to intersect this with the set of inequalities. Looks tedious, but what does it mean? The active inequalities. So what we already know has been sort of formalized in some fancy language. This captures that if you are at some point x and you want to, remember this is the linearized feasible directions at a point x, right? So x is over here. So you calculate this, the D which satisfies this together, both of these sets, is the D in which I can potentially move to. Then I have to see whether that D gives me an increase or a decrease and so on. That's the rest of the story. But this is the set of feasible directions as given by the constraints. Okay. So now let's revisit older example. Okay, which was simply x1 plus x2 was my condition, and the simplest case, which was x1 square plus x2 squared minus 2 equal to 0. This was our equality constraint, right? Let's draw this. Feasible set is the border of the circle. Okay. Now let us try to work out, for example, let's take this point over here. X is over here. I have taken this one point over here. I am purposely not taking the solution just to make it a little bit more interesting. So having this definition in mind, at this point x, remember this is at some point x. If I ask you what is D? How do I define it? What will we write? D transpose grad C1 equal to what? 0, right? So D transpose grad C1 equal to 0. This is the set of feasible directions, right? So let's open this up. What is D transpose? D is a two-dimensional vector because it's a direction in x1, x2 space. So I can simply write it as D1, D2 like this. What is grad C1? 2x1, 2x2. And I need this to be equal to 0. Right? So now what do I do? Substitute. What is this point? Minus root 2 comma 0. Right? So this is going to give me what? I mean, rather this will lead to, so if I substitute this over here, x1 is minus root 2. So d1 into minus 2 root 2 plus d2 into 0 equal to 0. So this is simply going to give me minus 2 root 2 d1 equal to 0. I just substituted the coordinates x1, x2 into this. So I got d1 equal to 0. So d1 has to be 0. So it tells me that at this point my set of feasible directions is 0 comma d2. d1 is 0, I am left with d2, and I didn't get any constraint on d2. So d2 could be any number. So I'll just simply write that as d2 belongs to the, lives in the set of all real numbers. Everyone with me so far? So what is this saying? If I were to draw this, if I ask you rather to draw this feasible set at this point x, what will you draw? A vertical line. Will that vertical line be up or down, or can't say? It should be up. Why? Is d2 belonging to plus r? No, we are not worrying about decrease right now. Just the set of the feasible directions don't take the function decrease, increase into account. It's just feasibility. So it's saying you can either, you're basically on this line, you could go up, you could go down, right? And that kind of makes sense because we know what is the solution to this guy, right? The solution to this problem is in fact this point over here. Now for me to stay feasible, I have to go tangential to the circle. I will go tangential. Between these two directions, which direction is the direction that makes sense? Minus x2. And that minus x2 is included in the two possibilities. So it kind of makes sense. If I had an algorithm, out of these two directions, it will pick the correct one going downwards. Okay. So great. So far everything is fine. So we are yet to decrease condition. Correct. Okay. Now I am going to do a little bit of a trick. Cheap trick. Very, very cheap trick. To break this connection that we have going on between algebra and geometry, I am going to leave geometry as it is, but I am going to change algebra a little bit in a very, very tricky way. C1x I have defined as, how have I defined C1x? x1 square plus x2 square minus 2 equal to 0, right? That everyone agrees is the border of the circle. Now what if I defined this instead? This is what I had, but now supposing I do this. Looks like a very cheap trick. Has the feasible set changed? Not at all. Geometry therefore is unchanged. But this is going to give us some strange problems with algebra. Okay. So let's relook feasible directions. Okay. What did I need for feasible directions? D transpose grad C1 equal to 0. This is what I am looking for. So D1, D2. This is my D vector. Now let's put down grad C1. So dC1 by dx1. What am I going to get? 2 times x1 squared plus x2 squared minus 2 multiplied by 2x1, 2 times x1 squared plus x2 squared minus 2 times 2x2. This whole thing should be equal to 0. At which point am I investigating this? The point is the same, right? Minus root 2 comma 0. What does this translate to? When I substitute this, I am in deep trouble. d1, d2, what does this evaluate to? 0 comma 0 is equal to 0, right? So, does this mean d1 equal to 0 or d2 equal to 0 or no? It means d1, d2 could be anything, right? So, this tells me that my feasible set is equal to, pick your favorite d1, d2, it satisfies these conditions, right? So, this we get a very important conclusion. Geometry is unchanged. I am at the same point satisfying the same constraint, okay? What happened to algebra? Changed in a very dramatic way, okay? In fact, it changed the set of feasible directions. From being constrained to just be that vertical blue line, now I am saying go anywhere in the plane, you are okay, right? So, algebra has changed, geometry is not changed, okay? So, there is something more that I have to do to algebra to make it be in sync with geometry. There is a missing link over there, right? Now, that missing link is what is called constraint qualification, okay? So, which we will talk about. So, you have to pass this through a filter, think of it as a filter of constraint to kind of restore the balance with geometry. Correct. To further terms, possible. Then I have to, yeah, I mean, this entire analysis is assuming first order conditions. Yeah, I did. So, if I were living with first order, it's like I have a toolbox that works only on first order conditions, and by doing this cheap trick, your tools stop working. So, before we go to second order, third order, remember going to higher orders is extremely expensive because then I have to calculate higher order derivatives. So, the very natural question people asked is, can we still make our tools work while staying in first order? So, these constraint qualification ideas, which we will talk about in the next session, they help us capture, they help us to retain this kind of a balance between algebra and geometry, right? Yeah, I think that's basically what I wanted to mention about this lack of sync between the two, right? So, hopefully you've all got an idea of when I say geometry what I mean and when I say algebra what I mean, right? Algebra is sort of just manipulating symbolically various symbols and expressions and getting a gradient or whatever out of it, and it conveys something. And geometry is what I am getting by looking at this drawing. Now, the drawing that I have done, it's okay for simple two-dimensional case. It's not going to work for something, you know, in n dimensions. So, we need to figure out a way to deal with that as well. Okay. So, we'll do that in the next session. So, any questions? Okay. Yeah. So, this definition of linearized feasible directions is simply formalizing what we already knew, which is what are the directions in which I can go so that I maintain, or rather so that I remain in the feasible set. That's all. For equality constraints. Second one, okay, so forget this math that I've written there. You can just say active inequalities. That you understand? Because let's go back to case 1 and case 2 earlier, which was here, right? So, the same problem. Case 1 was when x was inside this, right? At that point, if I ask you, what is a feasible direction? Feasible direction, I am not even interested in decrease. So I am sitting here in the middle or somewhere inside. I ask you feasible direction, what would you say? At least 0. C2x is strictly positive. So the second term can be actually anything as long as overall I am greater than or equal to 0. So basically what is it saying? There is no real constraint, you can be in any direction, right? So this is a constraint which is inactive. So I needn't bother about it because anything is possible. Well, greater than or equal to 0 needs to be satisfied. So I'm talking about the direction, not the length of the vector. So any direction will work. The total, as long as the total term is greater than or equal to 0. It can be negative also. According to the definition of feasible direction, this guy didn't appear only because this is an inactive constraint. This guy drops out of the discussion altogether. Exactly. That's why I need to be a little careful about active inequalities because it's if I take any direction, if I'm in case 2, if I take any direction when I'm in case 2, I'm in trouble. I can fall out, right? So that's why the final definition that we have of this scrolling is terrible, right? Of the linearized feasible directions takes care of the active inequalities. Because active set includes equalities and inequalities. If you look at the original definition, it has both. I've already caught the equalities above. So now I just want to pull out the inequality constraints, but I want them to be active. Yeah, it looks complicated to write, but we're just saying equalities and active inequalities. That's what. Constraint qualification, well, I haven't told you very much yet. We will discuss it in the next module. What we are saying is that by changing the constraint, by simply in this case, we just squared it. We found out that D transpose grad C1, it gave us nothing meaningful. It said take any direction. But we know that taking any direction here is not good because if for example, I go along the plus minus x-axis, I will become infeasible. So I don't want that to happen. So there is something shaky about this way of coming up with feasible directions. So I need one more kind of a filter to kind of tame it down. Those filters are called constraint qualification, which we will come to. I'm just giving you a trailer of what is to come. But we've identified the problem here that I squared it, I could take a square root of it, I could cube it, whatever. Or other ways of writing the same constraint will get me into trouble. And when someone gives you a problem, they may not filter and boil down the constraint in the most simple logical way. It may be written with a whole squared in it, you wouldn't really know. Yeah. Whether that point is a stationary point or yeah. So it's a test to subject a point x to. We have not discussed any algorithm. Okay. So it's kind of backwards in the sense that I'm not giving you an algorithm, but I'm giving you the convergence, like when you decide whether you want to exit the while loop of optimization. You check is norm of grad f small, is number of iterations exhausted, and then you quit. Similarly, here you have one, instead of grad f equal norm grad f being small, here you have these set of conditions which have to be checked. But I haven't told you what is in the body above it, right? So once we finish this discussion on first getting geometry and algebra into sync, okay, some techniques are there for that. After that, we will talk about one algorithm and the only algorithm that we will discuss in this course for constraint optimization, which is called the projected gradient descent method. This projected gradient descent method is an algorithm that tells you how to move from x to x plus s. And how to exit that algorithm is what we first spoke about. It's possibly the simplest constraint optimization algorithm.